So now we're going to do a set of examples that walk us through inter-process communication across different types of APIs and systems. The first example we're going to cover is actually going to be for POSIX systems. So that is going to be around the POSIX API, which of course includes all Unix variants, Linux variants, Linux distributions, as well as Mac OS. So in this particular example of inter-process communications, we're going to actually rely and use on the shared memory inter-process communication method. And when we leverage the shared memory method, there are a few distinct system calls that we need to implement or use in order, one, to set up our shared memory segment, and then also to set the size of that shared memory segment. In this case, it's a fixed size buffer, and then finally also to write to that shared memory, and then we will be also using a function called the mmap function, which establishes a memory mapped file containing the shared memory object. So as we can see here, the first step indeed is to use the shm underscore open, the shared memory open system call, to create the shared memory segment. We have to pass a parameter, essentially the name of the shared memory segment. That is a parameter that we pass, and then a few other parameters in the context of permissions. The next system call again is the ftruncate system call in this case, and with the ftruncate system call we're setting the size of the shared memory object. Let's jump into this a little bit deeper to get a feel for this, and one of the best ways that we've of course discussed in the past also to do this is really to look at the man pages on a POSIX system, for instance, so Mac OS being a POSIX system. Look at the man pages for these respective system calls. So when we look at the system call man page or the man page for the shm underscore open system call, we notice that clearly it gives us a nice description that the shared memory object referenced by name is open for reading and or writing as specified by the argument oflag, and the file descriptor returned to the calling process. Also, the return file descriptor will be the lowest non-open file descriptor for the calling process and is not shared with any other processes, as it is a new file descriptor. Okay, so with that in mind, we will be using the shm underscore open system call to open a shared memory object. Our next man page here is for the ftruncate system call, and what we're doing here is essentially leveraging this system call to set the size of the shared memory object. Moving on, the next system call we're looking at here, at least in the context of a man page, is the mmap system call, which allows us to allocate memory or map files to a device or device into memory. So specifically, the mmap system call causes the pages starting at the address location and continuing for up to the number of length of bytes, the len bytes, to be mapped from the object described by FD starting at byte offset offset. Okay, so this is the offset right here. This is our file descriptor, and then finally this is the starting address. Okay. So let's actually look at the producer code. So as we may recall from the previous section, in this particular shared memory interprocess communication example, what we have is a producer which is generating data, and then we will have a consumer code or consumer process which will consume the data. And these are two distinct processes. There's a producer process, there's a consumer process, and they of course have decided to share a shared memory region where the producer can keep populating that shared memory region with data, and the consumer essentially drains or consumes that shared memory region. If we were to look at this code a little bit further here, so we have a constant here which is defining the size of the shared memory object. Furthermore, we have a constant which really defines the name of the shared memory region. And then we have a few strings here which represent what will effectively get written, the strings that will get written to the shared memory region. Following that, we have a pointer to the shared memory object, and then we invoke, of course, our first system call here, which is to create the shared memory object, which has the name, nicely defined up there. The next thing we do is we configure the size of the shared memory object, which we've defined up top to be a constant of 4096 bytes. We look further at the next system call here, which is to memory map the shared memory object. And in this case, what we're doing is indeed starting at address position 0, as we discussed earlier, and we've specified, of course, the size to memory map that we had indicated. As we move a little bit further down, what we're doing is we're writing to the shared memory object with the sprintf function there, and we're really writing these messages to the shared memory object. Okay, let's keep going. Let's look now at the consumer. So that was the producer code, which of course when it executes will be the producer process. And now this is the code for the consumer process. As you'll notice, we have the same size for the shared memory object. We have the same name, important to note here. So both of those are identical. And then likewise, we are opening the shared memory object with the same system call, except that in this case we are opening the shared memory object in read-only mode. Because we are a consumer, we're going to be reading from this particular shared memory object. Likewise, we do a mapping to do a memory map, the shared memory object, and we still begin at address position 0, and we specify the size as we did in the producer process. And then finally, the last thing we're doing here is we use the printf statement to print essentially the contents that are being read from the shared memory object. And finally, at the end of our printing and reading, we remove the shared memory object with the shared memory unlink call. All right. So at this point, we can jump into a demo of this example, and we've just made a few modifications which will illustrate this set of code, both showing us both the producer as well as the consumer.